Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of particle physics with the course code PHY 452, we are at the lecture number 15 and the topic is quantum chromodynamics. In our previous lecture, we have developed the theory of quantum electrodynamics, which is the quantum mechanical theory of force between two electrically charged particles. We have developed then the procedure of Feynman diagrams and Feynman calculus to calculate the force. In our today's lecture, we will be building upon our previous knowledge of quantum electrodynamics and will develop a quantum mechanical theory of strong nuclear force between two particles. Strong nuclear force act only on quarks, so therefore in quantum chromodynamics we will deal with quarks. We will develop the Feynman diagrams and Feynman calculus. So we start with the primitive vertex example. Primitive vertex is actually a toy model which is very helpful when we want to consider complicated processes, because this Feynman diagram for primitive vertex helps us to understand the nature of the force. In quantum chromodynamics, as I told you, that we have only quarks on which the strong nuclear force acts. So therefore quantum chromodynamics is a theory of force between quarks. So in very simple example, as I said, it is a primitive vertex. We have a quark, and then this quark interacts with gluon. Gluon is the mediator of strong nuclear force, which we also call a color force. That's why the name quantum chromodynamics. In a moment it will be clear that these quarks carry a new kind of charge which is called a color charge. So together with the electromagnetic charge, which we are aware of, that is of plus and minus nature, we will have another charge over here as well, which we call a color charge. We will talk about this in a minute, but let's first develop a primitive vertex. So in this example we are saying that once there was a quark, okay, it comes and then it interacts with a mediator of this strong nuclear force or the color force. Nowadays it is called a color force, a gluon. In these Feynman diagrams we represent the gluons with the spring type line as compared to the photons which were represented with the help of zigzag lines. These gluons are represented with the spring lines. So these are the conventions. And then when quark comes and it interacts with the gluon and then it goes away. So this is a very primitive vertex. So you can think of a process that is once there was a quark which interacted with some kind of gluon and then it went away. So it is not kind of diagram or process which you will find in the nature, but this primitive vertex Feynman diagram and process will help us to understand and construct the real Feynman diagram for real process. So let's go for that and calculate the force between any two quarks. For this purpose, we have to know that in QCD, in quantum chromodynamics, as I already said, the color plays the role of charge. So we have electromagnetic charge, but we also have color charge, and it comes into three flavors or three types, that is red, blue and green. This does not have to do anything with the real colors, but it is just the aesthetic sense out of which Face is named the three types of the charges of the color charges as red, blue and green. So whenever there are two quarks and these quarks are interacting with each other, then we see that when there are two quarks, that is a quark 1 and quark 2, and they are coming and they are exchanging some kind of gluon between them. And what they do then when they exchange, for example, this quark have emitted or absorbed a gluon, and this quark has emitted or absorbed a gluon, and then another quark and two other quarks are emitted. So internal lines of this process is that there are two quarks coming, interacting with each other, either repelling or attracting, and they are going away with the two quarks. So this is force or interaction between two quarks, which is represented by the Feynman diagram. So you can see over here that we have combined two primitive vertices into one diagram to construct the interaction between two quarks. Next, we talk about the color charge. As I already mentioned, that there are three charges, that is red, blue and green. As compared to the quantum electrodynamics, there are only two kinds of charges, that is positive and negative. In color force or in the quantum chromodynamics, in strong nuclear force, we have three different types of charges, that is red, blue and green. So every quark will have can have a red, so quark can be, for example, a up quark can be having a red charge or a blue charge or a green charge. And similarly, gluons also carry charges. So a gluon can have a red charge, blue charge and green charge. So for example, in this process, you can see that, let's say if there was an up quark and this up quark had a charge of blue type. So this up quark is coming over here on this primitive vertex, and then it went away with changing its color or changing its charge, and now it went away with the red charge, red color charge. Since at any vertex the color must be preserved, the strong nuclear force preserves the color at any vertex, so this cannot happen that blue is changed into the red. So there must be another accompanying gluon over here, which must carry a kind of charge which preserves this red and blue over here. Now we also know that these gluons are bicolor, that they carry two colors at the same time. So they must be carrying such combination of colors that when combined with this up quark and up quark at incoming line and outgoing line, so that the charge is conserved over here. So you can see that blue was coming in and red was going out, but since in gluon there is an anti-red, so this anti-red actually cancels this red, and then at this vertex we are left with the blue charge. So in this way, that gluon is carrying the blue and anti-red color, is the color is conserved at the vertex, at the primitive vertex. So this will be the rule in the quantum chromodynamics, that at every vertex we will have color conserved. We will be taking care of such processes where the color is conserved. Okay, after this, as now we know that gluons can carry color, so it means that the two gluons can also interact with each other. Previously in quantum, this is the first difference between the or you can say the second difference. The first difference was the number of charges in quantum electrodynamics and quantum chromodynamics. So I will be telling you the differences between the two theories. In quantum electrodynamics we had only two types of charges, that is plus and minus, and quantum chromodynamics we have three types of charges, that is red, blue and green. This was the first difference. The second difference is that in quantum electrodynamics, the mediator, which was photon, was chargeless. So therefore two photons never interact with each other. But in quantum chromodynamics, since gluons are charged, they carry the charge, even they carry two charges, so therefore they can interact with each other. And this also gives, this difference also gives rise to very interesting phenomena. For example, having glue balls, because two gluons can interact with each other, therefore we can have the bound states of gluons, which are called glue balls. So gluon can couple to each other. So as I already said, since gluon carry color charges, they couple to each other. So there can be three gluons which couple. For example, there is a gluon, another gluon or another gluon. In this primitive vertex diagram, you can see a gluon is coming, gluon is going, and then there is another gluon which is emitted or absorbed. or you can have this kind of diagram where this gluon and this gluon is coming and these gluons are going away. So you can construct all first one vertex diagram or first order diagrams or two vertex diagram and so on. But the thing is that in quantum chromodynamics we can have two gluons interacting with each other. Then the third difference between two theories, that is quantum electrodynamics, that is QED, and QCD, quantum chromodynamics, the third difference is the size of coupling constant. Now what is coupling constant? Actually, coupling constant defines the strength of the force between two particles. If the value of the coupling constant is very high, then the force is very strong, and if the value of the coupling constant is small, then the force is weak. So now you can guess that in QED the coupling constant is actually the fine structure constant, and you can see over here that it is 1 over 137, which means that it is very, very small. So in QED the coupling constant is very small number, but in QCD and quantum chromodynamics this coupling constant is not small number, actually it's a big number and it is greater than 1. Now this fact is actually the source of a problem. And what is the source of the problem? Why it causes the problem? The reason is that when this number is very small, over here you can see this alpha E, then what we do, that we construct all sorts of Feynman diagram in QED. For example, we construct one vertex diagram, for example, and then all sorts of them, and then for any process, and then we have two vertex diagrams, and then we have three vertex diagrams, and so on. So this goes on. Now the thing is that in every vertex give rise to some kind of number, for example this coming from the alpha E. So when you have two vertex diagram, then since it's already a small number, so contribution from two vertex diagram is smaller than the one vertex diagram, and similarly the contribution from three vertex diagram is even smaller. So it means that we can construct the theory perturbatively, where we have one vertex, two vertex, and three vertex diagram, and so on. But since the contribution coming from higher orders like this are very small as compared to one vertex diagram, so we can neglect these higher vertex diagrams, and the main results come from here. Although these corrections have effects, but they are so small that we can just neglect them. But on the other hand, in the quantum chromodynamics, since this coupling constant is greater than 1, which means that when we have one vertex diagrams and then we have two vertex diagrams coming, then the contribution from higher vertex diagrams, that is two vertex diagram, are greater than the one vertex diagram, and similarly the contribution from three vertex diagram will be even greater than two vertex and one vertex diagrams. It means that we can no longer neglect the higher vertex diagrams, and it actually fails the Feynman method and Feynman diagram method and Feynman calculus for QCD. So this was a very source of concern, and physicists at that time were very concerned about that, because the very success of Feynman diagrams and Feynman calculus in case of QED could not be put forward or taken forward towards QCD. But fortunately this problem was solved by the phenomena known as asymptotic freedom. People have discovered the asymptotic freedom, where we found out that these complex constants are not actually constants. They are not really constants, but they are somehow running constants, which means that their values changes with the distance between two particles. So for example, if we have two particles and there is a distance between them, so if distance increases, so we have different kind of coupling between them, and if distance decreases, we have different kind of coupling between them. That's why we call them the running constant. So it depends upon distance, and this fact actually has given rise to another phenomena is called asymptotic freedom. And what asymptotic freedom means, that at very small distances the strong force becomes very, very weak, and then we can apply the Feynman calculus method to it and Feynman diagrams method to it, and we can calculate the strong nuclear force between two quarks. So in order to understand the asymptotic freedom idea, so asymptotic freedom at small distances, strong force is quite small, as I have already mentioned, that the idea is that at when distances are, that there is a coupling constant is running coupling constant, then when distances are small, then the nature of the force changes, and at very small distances the strong nuclear force is actually becoming weak. And this actually reduced the Feynman calculus method for a strong nuclear force. So in order to understand the strong coupling constant or the idea of asymptotic freedom, we need to understand the screening of charge in QED first. So this phenomena is like when you have like this positive charge over here, and you have let's say that this is some dielectric medium, and where there are molecules present, and there is a charge, positive charge in the center. Then what happens that in the surroundings, these all molecules are somehow polarized, and the negative side or negative pole is attracted towards the positive side, and the positive pole is repelled, and somehow this charge is screened over here. This is called the screening of the charge. So if you are standing here, then you will actually not look at the charge from there, because it is screened away from the negative charges. So the value of the charge over here is different than the value over here. We somehow call it the effective charge. So that this is the charge which is measured at the very large distances, or the distances outside the screening distance. And inside over here, the when somebody is here, then it will see the actual charge, but if somebody is here, it will not see the actual charge, but effective charge. And this comes because of the dielectric medium is polarized because of the presence of this charge. If we plot this one, you can see over here that this is the actual charge, and as the intermolecular spacing reduces, you go towards the real charge, and this q by epsilon naught is here. But as you go away, and at this time you have the maximum q by epsilon naught effect. So therefore the q effective is defined by q by epsilon, where epsilon is the dielectric constant or the measure of the power of medium to polarize the charges. The similar thing actually happens inside the quantum chromodynamics. You will be wondering that there is no medium present there, and there are no charges molecules to be polarized, but very interesting thing happens there, and this is the phenomena of vacuum polarization, where vacuum is actually polarized in electron positron pair. So this is, you can think of electron, and this is, you can think of a positron. So this is a vacuum, and this vacuum is actually polarized because of the two quarks present here. And now since it is electron, so it is attracted toward, so it's kind of a dipole over here, when electron is attracted towards one quark, and positron is attracted toward another one, and somehow vacuum is polarized. And when vacuum is polarized, so we are screening the charge, and at the larger distances we are not seeing the total charge, but at the smaller distances we see the actual charge. And you can see in these diagrams as well that there is kind of these are the 4 vertex diagrams, 4 vertex diagrams you can, or 6 vertex diagram, or you can see 2 loops over here. In these 2 loops diagrams there is also a vacuum polarization which is acting like a dielectric medium over here. So vacuum polarization is like dielectric medium and producing the poles, and these poles are producing the screening effect, somehow so to say screening effect. And at the end what you find out that the asymptotic freedom, because that at the very small distances the force between two quarks is almost negligible, and it is very small, the coupling constant is very small, and then we can apply the methods of Feynman diagrams. Over here the intermolecular spacing role is played by the Compton wavelength, which is of this order. So at this wavelength you see that the vacuum polarization happens. So as I already said that gluons also carry colors, so they must also be interacting with each other, giving us the gluon vertices, pure gluon vertices, where we have like over here you can see this is a gluon vertex, this is a gluon vertex. In this case you see that 3 gluons are here and 3 gluons are here. So these gluon vertices play very important role in order to determine the strength of the strong nuclear force. And we can also have different kind of gluon vertices over here, as you can see here, another gluon vertex. So the problem is that these gluon vertices are acting in the opposite direction in reducing the strength of the force. So when we decide about that how strong the force is, we also have to consider these gluon vertices. For this purpose, we need to define a critical parameter, and this critical parameter, which is actually the alpha, or these are some parameter, you can think of it like deciding whether the strength of the force is strong or weak. For this this formula, I mean it's a complicated formula to derive, but you can just note that this is this formula is correct. You can trust at the moment, and this formula is 2f minus 11n, where f are the flavors and n are the number of quarks present in the theory. And since we know that in standard model we have f is equal to 6 flavors of quarks and 3 actually quarks present, so if we put it over here, we get that alpha is equal to minus 21. So you see that the this critical parameter is very small. Therefore, at small distances, the strong nuclear force actually become very weak, and then we can, and the coupling constant is very weak, and then we can apply the Feynman calculus or the procedure of Feynman diagrams to calculate the force between two quarks. So in today's lecture we have seen that in quantum chromodynamics it is very similar to the quantum electrodynamics, but at the same time it has got some very important differences with the quantum electrodynamics. The first and most prominent difference is the difference of the number of charges, where we see that in quantum electrodynamics we had only 2 types of charges, but here we have 3 types of charges, and they are labeled as red, blue and green, and that's why we call them a color charges. And the second thing is that the mediators of the strong nuclear force, that are gluons, which are 8 in number, and this comes from the representation theory, this number 8, as contrast to the quantum electrodynamics, where there is only one mediator, that is photon. And the third difference is that photons are chargeless, they carry no charge, but gluons are actually charged particles, and they carry the color charge, that is red, blue and green. So this phenomena or this fact also gave rise to very interesting properties, like having glue balls and also having gluon vertices. And because of these gluon vertices, we have another phenomena which is called asymptotic freedom. Because of the asymptotic freedom, we were able to construct the Feynman diagram and Feynman calculus method for the quantum chromodynamics, because the coupling constant from quantum chromodynamics was very big, and we could not apply Feynman calculus method over there. But because of the asymptotic freedom and gluon vertices reducing this critical parameter value, actually has given us the procedure of Feynman calculus to be applied to the quantum chromodynamics. With this, I thank you all.